when you're dealing with projectile motion, and I want to really break this down. Everybody should have completed this question like midweek last week, okay? But I really want to break this down for us, that the most important aspect is that you have horizontal motion, which is uniform motion. And what I'm describing for you here is not just true for what we've learned and what we've been doing. It's going to be true for today as well. And you have vertical motion, which is uniform acceleration. And if you're sitting there going, yeah, no, I get this. Well, that's good. Then I've done my job and you've done your job, because that's the goal. You do not want to walk into your unit exam on Tuesday of next week and see a projectile motion problem and say, oh yeah, how did we do those again? It has to be like that. It has to be, I need to treat the two dimensions independent of each other. And I know that the horizontal motion is uniform, which means I can talk about velocity, displacement, and time. And these, although I don't need to do this, I guess I could, I think it's redundant to say V sub x and D sub x because it's in the x column, right? We don't need to do that. Whereas over here, since it's uniform acceleration, we have things like VI, VF, we have A, we have D, and we have T. And again, very redundant and almost a pain if we had to write all of these subscripts indicating it's Y. We don't need to do that. But I just want to leave it up there for a second for you to think about that any number that goes here on the left has to be a number associated with the horizontal motion. And in a question, and everything on the right has to be associated with a vertical. But sometimes, and you know how I feel about clutter, I think you know, sometimes more information is just clutter. It's like putting all the units in an equation where you're struggling to rearrange the equation because maybe you still haven't taken any Math 20. So your math skills have not been pumped up yet. So you leave the units out to make your job easier. So if you take a look at a question like this, can somebody work out what 140, well, all of you work out what 140 kilometers per hour is in meters per second? You're just going to divide by 3.6, and at this level we don't need to explain why that's the case. Sorry? 38.8 repeating? Okay. So what you would do is you would put that here. You can put the units in here if you like. I've got lots of room. And you would put 0 here. Because just like your lab, in the lab, that steel ball bearing left that long metal track, and at the instant it left contact with that track, it was traveling horizontal because I leveled the bottom of the track that way. So if it's traveling horizontally, just like this stunt driver is, then that 140 kilometers per hour is in fact the true initial velocity of the car, but it's at an angle of, we'll just say 0 degrees. I don't know whether it's east or west, it doesn't matter, or north or south. If it's at an angle of 0 degrees, then the component, this is a component of the initial velocity. The component that's vertical would be 0. What I'm going to say here is something I haven't said before. That this plus that these two velocities added together give me this. Not just because 38.8 plus 0 is 38.8. because 38.8 east and 0 north-south gives you 38.8 east. These are components of that original vector. But we didn't think of it as components because we just said, well, it's horizontal, so it's all horizontal. Are you with me on this? I'm not wasting my time here with this explanation. You're getting it? Okay. And then you fill in the other information. What do we know? Well, we know that this is negative 9.81. And again, so many students, so many classes, so many recordings, I lose track sometimes. I don't know that I've really pointed this out or in what fashion I have. In every projectile motion problem we have done, we don't need the negatives. Does that make sense to you? Because if VI is 0, then everything is downward. There's no up and then down. So if everything's downward, we could just use 9.81 and 70. But because I have chosen to put vector symbols here, and I've done it for a reason, we should put negatives. And I've done it because those days of ignoring them, that's about to end in today's lesson. We can't ignore them in today's lesson. What else do we know? I think that's it. But really, when you look at the right-hand column here, you have 3 kinematics quantities for accelerated motion. And that's enough to find anything else kinematically speaking. So the goal here is you could find the time in the air, use that over here because, again, it's not 2 cars. The car travels to the right and down at the same time. And then you can answer the question by calculating D. And I think that lab, I'm pretty sure that lab, the analysis reinforces how to do these problems. Just to see, does anybody have any questions from any of those problems? Yep. 7? Certainly. So a car moving too fast on a horizontal stretch of a mountain road slides off the road, falling into deep snow 43.9 centimeters below the road and 87.7 meters beyond the edge of the road. By the way, just looking at that, the fact that the horizontal distance is basically twice the vertical distance, that tells me the car was really moving. Okay. If you were in that car hanging onto the wheel when this happened, it would be a little bit of a terrifying experience. How long did it take to fall? And also, how fast was it going? So I'm just going to cover these up. What we do, of course, is we set up our table where we have X and Y. I'm not going to write that X is uniform motion. We should know that. If this were any kind of a written assignment, you'd probably write uniform motion. And I'm not going to put vertical motion here. So we have V, D, and T. Although I can always get away with ignoring the vector status of V and D under horizontal, I'm going to put it anyway. And although in this case we can get away with ignoring the vector status of these, we can always ignore the vector status horizontally, always. In this question, we can ignore the vector status vertically, but we can't always. Okay. And then, of course, we have our time. And the thing, of course, that connects the left-hand part of the column with the right-hand part of the column is that these 2 times are equal, right? So what do we know? Well, we know A is negative 9.81. And I'll leave the units out. In addition, I don't need negatives here. I don't. But since I put vector symbols, I'm going to put them anyway. If the via 43 meters below the road, yeah. I hope the airbag went off at some point during this. 43 meters below the road, that's half of a football field essentially. But if the snow was 43 meters below the road, that means the vertical displacement of the car is negative 43.9 meters. It's negative because it's below. I said I'd leave out the units, so I'll leave out the units. VI, of course, is 0 because, and I want to drill down a little deeper here, that if this is the car, and here well, it's cartoonish in nature, I get that. And here is the initial velocity, which is unknown, some speed. Let's just call it a number. Don't confuse this that I've written here with this VI under the Y. This that I've written here is the true velocity of the car. Maybe it's 29.9 meters per second in that direction. 29.9 meters per second in that direction means it will be 29.9 meters per second under the x column and 0 here. In other words, this is the vertical component of that. Right? This is overkill. I do not need to write that. You do not need to write that. But it's leading up to what we're going to do today. What else we know? We know that the car travels 87.7 meters to the right. What are we asked to find? We are asked to find two things specifically. I think, does the first thing say how fast was the car moving? Or does it say find the time? Yeah, because you have to find the time before you can find the speed. So one of the things we have to find is this, and the other thing we have to find is this. So looking at it from a formulaic standpoint, there's not enough information in the left-hand column for us to calculate V or T. But looking at it from a formula standpoint here, we can use this formula to find the time. Two times the displacement over the acceleration will be t squared. So we have to take 2 times the displacement divided by the acceleration and then take the square root. That will give us the time. Then we will know the time here as well, so we can find the speed here. So let's just finish it off and see what we get. 2d. See, and here I'm not even going to put in the negatives. I don't think they're going to cancel. So just from a math standpoint, I wouldn't put them in. Okay, 2 times, what was it? 43.9 times 2 divided by 9.81, and I take the square root. You'd be surprised how easy it is to forget to take the square root. So 2.99 seconds. That time now is the time over here as well. And if I want to find the speed, I can take that distance and divide by that time and get 29.3 meters per second. It's over 100 kilometers per hour. So the car, as it travels through the air, will be traveling at 100 kilometers per hour this way, over, while in free fall vertically. And either one of those is scary. Put them both together, pretty scary. Any other questions? Does that help? Okay. Any other questions? All right, we're going to take a look at page 43 now. And again, I'm not in a big hurry here. I know from experience that there are certain topics in Physics 20 and certain topics in Physics 30 that students struggle with, and this is one of them. We're looking at part 2 of projectile motion. I say that because I don't want to rush through this. We've got lots of time. We're going to be solving problems that involve projectiles that are launched at an angle, a non-zero degree angle. So whether they are launched up or down, it doesn't matter. We typically solve problems in which the projectiles are launched upward at an angle. So, and this is from the previous lesson. I feel as though I can kind of rush through this because I just spent a lot of time talking about this. Recall that when we solve projectile motion problems for objects launched horizontally, the initial vertical component of the velocity is 0, and the horizontal velocity is whatever the speed of the object is launched at. So again, when you look at this diagram and you see on here that this is 4 meters per second, I'm not saying that's the horizontal velocity. I mean, it is. But what I'm saying is that's the velocity of the car to begin with, 4 meters per second in that direction. And when you tear it apart into components, you put the 4 meters per second as v for x because the horizontal component of that blue velocity is 4. It seems as though I'm saying something that doesn't need to be said, but I'm going to say it anyway. When you take this and you break this into a horizontal component and a vertical component, the vertical component is 0 and the horizontal component is 4, right? Why is it that this 0 for the vertical component ends up being VI? Well, because vertically speaking, it's about to change. That vertical velocity will not continue to be 0 meters per second. Why do I not put an I for the V for the 4 meters per second? Because it's uniform motion that way. It's always going to be 4 meters per second that way, but the velocity downward is going to go from nothing to an increasing value downward. When we launch an object at an angle, there's just one additional step. The problems get more difficult as well. But the additional step in setting up that chart is to find a horizontal and a vertical component of the initial velocity. And when I say of the initial velocity, I'm not talking the initial vertical. That's what we're trying to find. I'm talking about the initial velocity. So we're going to do a couple of examples today, and then we're going to practice some problems. I also have a couple of challenge problems because I know that some of you might enjoy trying to crack them. So number one is a classic question. There's two main types of projectile motion problems in this lesson. A ball is thrown at a particular speed with a particular direction above the horizontal from the ground. It doesn't say this, but it's from the ground. So you have some type of method of launching an object off of the ground at an angle with a particular speed. How long is the ball in the air, and what's the maximum height of the ball, and how far away does it land? This is the classic problem in projectile motion. And then there's a more complicated one. So what's happening here is the object starts here. It's launched at an angle of 38 degrees. At 18 meters per second. The biggest, well, I don't know if it's a misconception, it's just something that people do without even thinking. The biggest problem here that students have is not realizing that that arrow does not represent the direction the ball will follow. It's the direction the ball has at this instant. As soon as a millisecond goes by, the angle is going to go from 18 or 38 degrees to some smaller angle because gravity will be pulling it down. So what happens is the ball follows this kind of trajectory. That's not bad. It's a little bit off, but I hope you understand, based on the work we did in earlier parts of this course, that this path will be symmetrical. That is to say, it's going to land at 18 meters per second at 38 degrees down. And the time it's going to take for the whole journey will be twice the time it takes to get to the top. Right? It's going to be in the air rising just as often as it is falling. And we have done problems where objects are thrown up and they rise and then they fall. How is this different? It's rising and falling while traveling to the right at a constant speed. It's two things being put together. And the question is basically this. Well, it's three parts. What is that height? What is this distance, which is often called the range of the projectile? And by the way, and it's not drawn perfectly, this distance and this distance should be equal. Gravity doesn't change while the ball's in the air. It's going to act on it, giving the same negative effects while it's on its way up as the negative effects when it's on its way down. Gravity is negative everywhere. And then also you want to find the total time to impact. So these are the three things we need to know, we want to find. But there's an issue here, and that's that the total time in the air doesn't correspond. The total time in the air corresponds to the total distance. It does. But the total time in the air does not correspond to the maximum height. Are you with me on that? So my idea, not mine, but my suggestion to you is always go with the maximum height. It gives you the most opportunity to know things about the motion at the maximum height. And then if we can find the time to the maximum height, we'll just double it to get the total time in the air. And if we can find the horizontal distance to the maximum height, we'll just double it to get the total range. So we're going to set up our table using this diagram. Oh, no. I just want to give myself a little more room. So what's our table going to look like? It's going to contain the exact same sets of variables that we have always put in here. We have an x and a y. We have a v, a d, and a t. Under x. Under y, we have a vi, a VF. Now, I don't know if this really has occurred to you, but you understand that all the projectile motion problems we've been given so far, we didn't care about VF? Okay. There is also a D. There's, of course, the acceleration due to gravity, which we'll put in a second, we know the value of, and there's a T. So what we can do is, well, let's put it in now. This is negative 9.81. And VF is 0. VF is 0 vertically. I am going to be talking about this point in time. That's the point in time I'm interested in. So when I get a time in this calculation, it's going to be the time to that point. When I use that time to that point to find this horizontal distance, that will be half the total distance. And that time will be half the total time. But when I find d under vertical, that will be the maximum height. And by using that point at the top that I've indicated, it allows you to say VF is 0. Sam, we had this conversation a couple weeks ago about just vertical motion up and down, and it's always best, if it's up the same amount as it is down, to just go with half the trip. Then you can say VF is 0 somewhere. The issue is this 18 does not go here or here. That 18 is not either of those. That 18 is those two vectors added together. So you need to draw, well, you don't need to, but I'm going to draw that vector off on the side. Because we need to find the horizontal component of that vector and the vertical component of that vector. This horizontal component, everybody, is v in the x column. And it's going to be whatever that number is throughout the whole journey because there's no gravity acting left or right. This vertical component of the initial vector, of the initial velocity, will be the initial vertical component, which is vi in the y column. And we have to say I because it's going to change, because gravity is going to affect it. This is the additional step I've talked about. So I'm going to give everybody a minute here to calculate those numbers, and you can write them down to 1 or 2 decimals. It doesn't really matter to me. At this point in time, I had muted my mic and forgot to unmute it, so I'm just going to narrate the remainder of this video. What you need to do is calculate the horizontal and vertical components of that vector that's drawn in the bottom right of the screen. The adjacent side is associated with cosine, which will give us the horizontal component, and the vertical side is associated with sine, which will give us the vertical component of the velocity. So what I'm really doing is just solving that triangle in the bottom right. The horizontal component is 14.18 meters per second. The vertical component is 11.08 meters per second. The vertical component is pointing towards the sky, so I'm going to assign that as a positive. I'm also assigning the horizontal component of the velocity, that 14.18, as being positive. But, I mean, that's neither here nor there. If the object had been launched up and to the left, I probably still would assign that a positive value. At this point in time, you know on the vertical side of things, the initial velocity, we're using VF equals 0, don't forget, because that's going to take us to that middle point, which corresponds to the maximum height. So if you use VI equals that vertical component of 11.08, VF equals 0, and the acceleration due to gravity is negative 9.81 meters per second squared, then you can find either T or D at this point in time. I believe in the lesson that I found the displacement first. And I'm going to be using the formula VF squared equals VI squared plus 2AD. So when I put in the numbers, VF is 0, so I get 0 squared, or 0, equals VI squared plus 2 times negative 9.81 times D. So this results in the equation 19.62D equals 11.08 squared. So we need to take that 11.08 and square it, and then divide by that 19.62. So putting all of the numbers into VF squared equals VI squared plus 2AD gives 0 squared, which is just 0, is equal to 11.08 squared plus 2 times negative 9.81 times D. Simplifying that a little bit gives 0 equals 11.08 squared minus 19.62D, which means 19.62D is equal to 11.08 squared. So to solve for D, we're going to have to take that 11.08 squared and divide by 19.62. And what we're getting is 6.259, or about 6.3. Once again, since we used VF equals 0 in the vertical column, and we've calculated D vertically to be 6.3 meters, that's the maximum height of the ball. Now what we can do is we can find the time. Don't forget, one of the things you're trying to find in this question is the total time the ball is in the air. If you stick with the chart that you're looking at on the screen right now, which I would recommend, when you determine that time, where it says T equals, that time will not be the total time in the air. That's only going to be half the time. So the formula I'm writing down on the right-hand side of the screen is the formula that I prefer to use at this point in time. Since VF is 0, the equation becomes time equals negative VI over the acceleration due to gravity, which is a pretty simple calculation to do. We already have that VI, it's 11.08, and we know the acceleration due to gravity is negative 9.81, so the next step would be to calculate that time. So I'm just going to do this on another part of the screen. The acceleration is negative 9.81. VI is positive 11.08. So we have to take negative VI, which is negative 11.08, divided by A, which is negative 9.81. We're going to get a little over a second here, it looks like. I'm probably just going to leave out the negatives when I do the division because they're going to cancel. So 11.08 divided by 9.81 gives about 1.13 seconds. Don't forget, and I'm going to probably write that into the chart, there it is, 1.13 seconds. That's only half the total time. The question did ask, what's the total time that the ball is in the air? So what we're going to do is multiply that number by 2, and then we will have an answer for that part of the question. So far we have the maximum height is 6.3 meters. The total time will be equal to 2 multiplied by 1.13 seconds. Now I wrote meters there. We're going to catch that in a second, or I'm going to catch it. It's actually seconds. And that gives a total time up and down of 1.129 seconds up and 1.129 seconds down, gives approximately 2.26 seconds in the air total. So this means that the object is traveling to the right at 14.18 meters per second for 1.129 seconds to get to the halfway mark. So if you take that 14.18 meters per second and multiply by that time, you will be getting half of the horizontal distance that the ball travels, which is not what we're after. So I've multiplied that time by 14.18 meters per second, and I get 16 meters approximately. So that horizontal distance of 16 meters is only half of the total distance. So to finish the problem, all we have to do is double that horizontal distance of 16 meters and get an answer of, I guess, what's going to be 32 meters. I assigned numbers 1, 2, 4, and 5 on the attached assignment. That's as far as we got. We finished that first example, and in the next lesson, we are going to be looking at least one more example.